In this segment, we're going to talk about multi-stage vapor compression refrigeration with intercooling. So from 1 to 2, you've got an ideally isentropic compression process. And you'll notice this 1 minus x here on the diagram. So this indicates that not all of the flow is going through that compression process. Sort of like when we talked about the Rankine cycle with regeneration with the open feed water and the closed feed water heater. You had the flow splitting up and you had to count for that. This is what we're doing here. So we're splitting up the flow, and 1 minus x represents the proportion of flow that's going through that compressor. Then you go into this direct contact heat exchanger. So you've got a hot stream that's coming in at 2, and then it combines with a cold stream, which is coming in at 9. And you can see the proportion of refrigerant that's coming in at 9 is x. So these are the two portions of refrigerant that were split up, and now they're joining together. They're happy again, and they're coming out at some temperature in the middle. So T3 is in the middle of T9 and T2. All right, then it goes into another isentropic compression process from 3 to 4. So what we've done here is we've divided up one compression process into 2 compression processes. So if you looked at a simple vapor compression refrigeration cycle, you only have one compression process. Here we've divided it up into 2, and we've put intercooling in the middle of them. So we've partially compressed it from 1 to 2, then we've cooled it down, and then it's fully compressed from 3 to 4. And at state 4, your temperature's high, it goes through your condenser. So the temperature of your refrigerant flowing through that condenser is higher than the temperature of that high temperature reservoir, whatever environment this refrigeration cycle is sitting in, and it rejects heat at constant pressure all the way to state 5, and it exits that condenser as a saturated liquid. Then you go through an ideally isenthalpic throttling process, and what comes out of that throttling valve is two-phase. So you see state 6 on the TS diagram is in the two-phase region, so you've got a proportion of that refrigerant is a saturated vapor, and the other portion is a saturated liquid. And it goes into what's called a flash chamber. And the purpose of the flash chamber is to separate those two phases. So the saturated vapor goes on to state 9, and you can see that this proportion is x. And then the rest of it is allowed to be gravity fed. Liquid's heavier, so gravity fed out the bottom. Saturated vapor continues on its merry way, and we're going to see that in just a second. But let's kind of focus on this state 9 here. So the proportion that comes out of that flash chamber as a saturated vapor, this is x, and it's equal to the mass flow rate at 9 divided by the total mass flow rate, so m dot. And m dot, the total mass flow rate, is equal to m dot 3, m dot 4, m dot 5, and m dot 6. And because the quality at state 6, the quality of the incoming refrigerant to that flash chamber represents the proportion of your two-phase mixture that exists as a saturated vapor, well, that proportion x is just equal to the quality at state 6, the quality of the incoming two-phase mixture. And let's see. All right, let's keep on going on our merry way. So the saturated liquid is gravity fed out the bottom. That's state 7. And the proportion of saturated vapor that's coming out is just 1 minus x. And the mass flow rates on the bottom loop, which we'll see it completed in just a second, are all equal. So m dot 7, when we get to it, m dot 8, m dot 1, and m dot 2 are all equal to one another. Now let's look where our pressures are equal. So this flash chamber is a constant pressure, not process, but the pressures of the incoming and outgoing streams are all the same. So P6, P9, and P7, on the left-hand side you see 6, 9, and 7 are all exactly the same. But then you look at the direct contact heat exchanger. So this is it's a mixing chamber. So the incoming and outgoing pressures there should be approximately the same too. So P2, P9, P3 are equal to one another. So what you see is you've got a whole bunch of pressures in the middle of this schematic here that are equal. So 6, 9, 7, 3, 2, all of them are equal. All right, so let's finish up our cycle here. So from state 7 to state 8, you've got an ideally isenthalpic throttling process. So you've gone from a saturated liquid to a saturated vapor, or saturated vapor, I'm sorry, a two-phase mixture. And that two-phase mixture is fed into the evaporator, and it undergoes a constant pressure phase change all the way to a saturated vapor. And it's removing heat from that refrigerated space at constant pressure. So the temperature of your refrigerant that's flowing through that refrigerated space should be lower than the temperature of your refrigerated space, so heat will flow into the refrigerant. All right, now, if what we did is just did this with a simple vapor compression refrigeration cycle, so we didn't divide up that compression process into two, we just did it once. So we've compressed from state 1 all the way up to, we're going to call it state 4, just to kind of keep the numbering the same. So what we would have to do, you see that we'd have to compress all the way to state 4, to P4 in one process. And if you compare that to the diagram for the multi-stage compression, vapor compression refrigeration cycle with intercooling, if you compare that TS diagram, what you see is that it's going to take more compressor work to compress in one process rather than just dividing it up into two. All right, so we're almost done here. Let's look at our Q dot N. So our Q dot N, when you calculate that, what that is, you have to factor in that not the whole mass flow is, only a portion of the refrigerant is going through that evaporator. So you need to multiply this by 1 minus X. And if you need a little bit of a refresher on how we calculate all this, I would suggest that you go back and review the calculations for the Rankine cycle with regeneration, with the open feed water heater and the closed feed water heater, and make sure you see how we got here. And once again, you can see where the mass flow rates are equal. M dot, the total mass flow rate, is equal to M dot 3, 4, 5, and 6. So that's Q dot N. The only other thing, I guess, that it's a little bit, might be a little bit weird is the W dot N, or the W dot net N, we should call it. And this is the work for that bottom compressor plus the work at that top compressor. So the work at the top compressor is, or the power of that, the required by that top compressor, is just M dot times H4 minus H3. But the bottom one, you don't have all the flow going through there, so you need to multiply that portion by 1 minus X. And once again, if you do need a refresher on that, I would suggest that you go back and look at the Rankine cycle with regeneration and see how we calculated those things. All right, well, I hope that was helpful. We'll work some problems the next time we meet.